Assalamualaikum and good day. Today we will learn about solar photovoltaic, chapter 3. Let's go through the table of contents. Number 1 is introduction. Number 2 is structure of PV module. Number 3, we will learn about advantages and disadvantages of PV power system. Number 4, application of PV modules. Number 5, PV cell characteristic. Number 6, efficiency of the conversion. Number 7, testing standard. Number 8, factors that affecting the power output. Number 9, predicted voltage, current and power of PV module. And lastly, the bypass diode. So the introduction. Solar cell or photovoltaic cell, which are foundation of PV system, convert the energy in sunlight directly into electricity, which is in a DC form. Consequently, the fuel is free, but the term photons come from the Greek phos, which means light, and volt is the name of Alexander Volta, a pioneer in the field of electricity. So electricity is produced when sunlight strikes the semiconductor material, for example silicon, in a photovoltaic solar cell, which is creating an electric current. Photovoltaic energy system can be as small as a few solar cells or as big as large array of PV modules, which are made up of interconnected group of solar cells. So whether the solar cell is connected in series and parallel. In general, we have 4 types of PV technologies, which is monocrystalline, polycrystalline, TinFilm, and HIT. Okay, we start with monocrystalline. The advantages of monocrystalline are highest efficiency rate since they are made out of the highest grade silicon, which is 99.99% pure silicon. The efficiency rate of monocrystalline solar panel are typically 15 to 20%. SunPower, the name of the company, produce the highest efficiency solar panel on the US market today. Their E20 series provide panel efficiency of up to 20.1%. So in April 2013, SunPower has released this X series PV module at a record-breaking efficiency of 21.5%. But nowadays in 2020, SunPower again breaking the record, produced the most efficient panel on the market, which is the efficiency is about 22.8%. For monocrystalline, lower temperature coefficient compared to polycrystalline, which is under standard test condition. Example here, lower temperature coefficient, which is 0.30% per degree Celsius. What does it mean by 0.30% per degree Celsius? Means, for example here, the power temperature coefficient, which is minus 0.30% per degree Celsius, which is the power will drop, minus is a drop or reduce, 0.30% every 1 degree Celsius. For voltage temperature coefficient, also minus means drop or reduce, minus 167.4 millivolt for every 1 degree Celsius increment. So current temperature coefficient, this is opposite of power and voltage, which is when the temperature increase, the current will increase. That's why you have this positive or no minus symbol here. So every 1 degree Celsius, the current will increase 3.5 milliampere. So this temperature coefficient is good compared to the polycrystalline. means when the temperature increase, the reduction of the power and the voltage, which is less than polycrystalline PV module. So here we have two model. Okay, let me zoom in. So two model here. Example here we have nominal power, P nominal, and power tolerant in percentage plus 5 mean the power increase 5%, but minus 0% means there is no reduction on power. Average panel efficiency 21%, this model 21.5%. This is rated voltage or voltage at maximum power point, VMPP. And here is the rated current or current at maximum power point, IMPP. So compared to this model have the highest current compared to T35 BLK. Open circuit voltage, VOC. Short circuit current, ISC. Maximum system voltage is 600 volt and 1000 volt standard IEC. This is standard UL and standard IEC. Okay, we follow Malaysia, which is we use IEC. So maximum system voltage is 1000 volt, means when you make a parallel connection of not parallel connection, a series connection of the PV module, make sure it's not exceed 1000 volt. Okay, because when you sum up the voltage from the PV module, okay, let me draw here. So this is your PV module. This is the symbol. So the cover like an envelope, the cover of the envelope is positive and this is negative. For example, here you take VOC for this model is 68.2. Okay, you sum up all. So make sure in the series connection is not exceed 1000 volt. So 68.2 plus 68.2 and so on. So make sure in the series connection it must be less than 1000 volts. So that's mean for this one. Maximum series fuse 15 ampere. So when you make a series connection, okay, let's say this is IAC. IAC, if you make a short circuit current here, so your current must not exceed the maximum series fuse. So the maximum one is 15 ampere. So here the ISC is about 6.39. But if you make a two parallel connection, okay, let's say you have another parallel connection here. So you will sum up these two current, right? So 6.39 plus 6.39, which is less than 15 ampere. So you sum up, which is okay, less than 15 ampere. So the maximum series fuse, which is 15 ampere. Okay, you can make it. The fuse, we have two fuse. One fuse at the array junction box Okay. Another one is fuse here. We call a series maximum series fuse or string fuse. Okay, let me draw again here. Usually we put fuse Okay, this one we call string fuse. So when you make a parallel connection, we have another fuse here. Let's say this is not short circuit. So we connected to the array junction box. You have another fuse. Okay, space efficient. For this monocrystalline, of course, the size is small with the same power. The size is smaller than polycrystalline and TinFilm. Since this solar panel yield the highest power output, they also required the least amount of space compared to any other types. Live the longest, which is most solar panel manufacturer put a 25 years warranty on their monocrystalline solar panel. However, this warranty depends on the manufacturer because it have this extra charge, extra amount that you need to pay to have this warranty. Tend to perform better than similarly rated polycrystalline solar panel at low light condition, mean at the low solar irradiance. So disadvantages, the most expensive. The Kozarski process is used to produce monocrystalline silicon. Okay, let's see the video here. Okay, copy the video. Let me find here. Okay, please make sure you watch the video for the Kozarski process because I cannot click here. It's just a simple video on this Kozarski process. So they have this monocrystalline rod, this one is created by slowly pulling a monocrystalline silicon seed crystal out of melted polycrystalline silicon, which is 99.99% pure silicon. It results in a large cylindrical ingot. So this is the large cylindrical ingot. 4 sides are cut out of the ingot to make silicon wafer. A significant amount of the original silicon end up as waste. So this shape, let me redraw the cylindrical ingot. So they cut this one, so it will become this shape. Let me draw bigger than that one. Oh, no. Okay, so they cut into this shape. Why they choose this shape? Because this shape can make the waste less compared to the other shape. Okay, so this one become the waste. So all this the wasted silicon. Why they choose this shape? Let's say you choose a perfect circle, perfect square. Of course, the waste is more than this one. Okay. So this waste is greater than this kind of shape. Okay, we continue. So monocrystalline solar panel tend to be more efficient in warm. It's a warm, not a hot climate. For the hot climate, the suitable one is the TinFilm. But the performance suffer as the temperature goes up. Okay, when the temperature goes up, of course the voltage will drop. So this is how the monocrystalline looks like. So we have 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. 6 multiplied with 4, 24 solar cell of monocrystalline, monocrystalline solar cell. Okay, next PV module we call polycrystalline. The advantages is the process used to make polycrystalline silicon is simpler and cost less, thus cheaper compared to the monocrystalline. Okay, they then use this Kozarsky process. So they use raw silicon, which is melted and poured into a square mold, which is cooled and cut into a perfectly square wafer. Okay, so they use a square mold and then they trim to the square shape. So this is the polycrystalline compared to the monocrystalline solar cell. So the amount of waste silicon is less compared to the monocrystalline because they make it in the square mold. Okay. So the disadvantages, polycrystalline solar panels tend to have slightly higher temperature coefficient for power than monocrystalline solar panel. This technically means that they perform slightly worse than monocrystalline solar panel in high temperature. And the efficiency of polycrystalline based solar panel is typically between 13 to 16%. Because of lower silicon purity, polycrystalline solar panel are not quite as efficient as monocrystalline solar panel. Lower space efficiency. You generally need to cover a large surface to output the same electrical power as you would with a solar panel made of monocrystalline silicon. Monocrystalline and thin film solar panel tend to be more aesthetically pleasing since they have more uniform look compared to the speckled blue color of polycrystalline silicon. If you compare in this picture, they have this speckled blue color, but for monocrystalline, they have this uniform color. This is because this is from the raw silicon and this is from the pure silicon. So this is how the polycrystalline PV module looks like. Okay, here we have 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 multiplied with 4, 36 solar cell per PV module. Okay, next one is thin film. Depositing one or several thin layers of photovoltaic material onto a substrate is the basic gist of how thin film solar cells are manufactured. They are also known as thin film photovoltaic cells, TFPV. The different type of thin film solar cell can be categorized by which photovoltaic material is deposited onto the substrate. First, amorphous silicon. Second, cadmium telluride. Third, copper indium gallium selenide. And lastly, organic photovoltaic cells. Depending on the technology, thin film module prototype have reached efficiency between 7 to 13%, and production module operate at about 9%. Future module efficiency are expected to climb close to the about 10 to 16%. Advantages: cheapest module but lowest efficiency. However, better temperature coefficient for power, which is the power only drop minus 0.2% per degree Celsius. High temperature and shading have less impact on the solar panel performance. The mass production is simple. This make them potentially cheaper to manufacture than crystalline-based solar cell. Their homogeneous appearance makes them look more appealing. So they have a uniform color, just like monocrystalline. Can be made flexible, so they can be folded, which open up many new potential applications in situations where space is not an issue. For example, in the desert, thin film solar panel can make sense. So the disadvantages is require a lot of space compared to mono and polycrystalline for the same power rating. Low space efficiency also means that the cost of PV equipment, so other than PV module, they have a support structure and the cable will increase. Thin film solar panel tend to be degrade faster than mono and polycrystalline solar panel, which is why they typically come with a shorter warranty. Solar panels based on amorphous silicon, cadmium telluride, and copper indium gallium selenide are currently the only thin film technologies that are commercially available on the market. Okay, let's see number 1, amorphous silicon solar cell. Because the output of electrical power is low, solar cells based on amorphous silicon have traditionally only been used for a small-scale application, such as in a pocket calculator. However, recent innovation have made them more attractive for some large-scale application too. With a manufacturing technique called stacking, several layers of amorphous silicon solar cell can be combined, which result in higher efficiency rate, typically around 6 to 8%. Only 1% of the silicon used in the crystalline silicon solar cell is required in amorphous silicon solar cell. On the other hand, stacking is expensive. Number 2 is cadmium telluride solar cell. Cadmium telluride is the only thin film solar panel technology that has surpassed the cost efficiency of crystalline silicon solar panel in a significant portion of the market for a multi-kilowatt system. So the efficiency of solar panel based on cadmium telluride usually operate in the range of 9 to 11%. The company First Solar has installed over 5 gigawatt of cadmium telluride thin film solar panel worldwide. The same company holds the world record of cadmium telluride PV module efficiency of 14.4%. Okay, the next one is copper indium gallium selenide CIS or CIGS solar cell. Compared to the other thin film technology above, CIGS solar cell have shown the most potential in terms of efficiency. This solar cell contains less amount of toxic material cadmium, which is found in the cadmium telluride solar cell. Commercial production of flexible CIGS solar panel was started in Germany in year 2011. The efficiency rate of CIGS solar panel typically operate in the range of 10 to 12%. So many thin film solar cells are still early in the research and testing stages. Some of them have enormous potential and we will likely see more of them in the future. So this is how the thin film looks like. They have a uniform color and they don't have this shape of the solar cell because this is a thin film. So this is a solar cell of the monocrystalline. So in this solar cell, they make the connection of series and parallel. And this is the polycrystalline PV module. Okay, another one is HIT, heterojunction with intrinsic thin layer. Okay, the first company that introduced this HIT is Panasonic. Hybrid technology which combination of crystalline and thin film. So crystalline, they have more power, and thin film, they have more power when the temperature is increased. better temperature coefficient approximately. For example here, for the power will reduce 0.30% per degree Celsius. So this is the typical type of the PV module. So we have P-type, and this is the non-regular grid area, and this is the crystalline silicon P-type. But for this one, they have a clean surface, which is minimal non-regular grid area, okay, on this surface, and they have this N-type. So N-type amorphous, okay, on the top, and the P-type amorphous on the below. So figure layer of HIT PV modules. We see the temperature coefficient here for power, which is 0.30%, and also temperature of voltage, temperature coefficient of voltage, VOC, which is minus 0.126 volt per degree Celsius. So every 1 degree Celsius increment, the power and voltage will drop under this tolerance. So temperature coefficient ISC is 1.76 milliampere per degree Celsius. So what happened to this HIT? So the below the bottom layer will extract the heat. For example, we have rooftop. So this one will extract the heat or absorb the heat to produce the electricity, and the above one will absorb the sunlight. Okay, so that's why they have this two layer here. So this is example of the HIT. Okay, missing H here. HIT module. Okay, example here. So this is the shape of the module, which is a hexagon. Okay, another type of PV module is solar PV combined with the solar thermal. So we have PV module, at the same time we have this pipe, okay, for the solar thermal. So that pipe is to produce the heat. Example here, progress development of PV cell technology as follow. So this is the graph for multi-junction cell. Okay. So this multi-junction cell produce the highest efficiency. Okay. But remember back, even though TinFilm they said have the lowest efficiency here compared to the amorphous silicon. Okay, amorphous silicon is the TinFilm technology, which is in this area. So the efficiency is lower than crystalline silicon, the blue color, and the multi-junction cell, okay, the purple color. Okay, structure of PV module. So we start with the top of the PV module. We have cover glass, protect the cells from damage, and then EVA. EVA is the ethylene vinyl acetate, EVA. And then this is the solar cell, the third layer, and then again EVA below the solar cell, and then the back sheet, and then the junction box. So in this junction board they have this bypass diode, and also they installed the cable MC4 and the cable. Advantages and disadvantages of the PV power system. PV system can be designed for a variety of application and operational requirements and can be used of either centralized or distributed power generation. PV system has no moving parts. So no moving part, for example, the PV system installed with the fixed structure are modular, easily expandable and even transportable in some cases. Energy independence and environmental compatible are two attractive features of PV system. The sunlight is free and no noise or pollution is created from operating the PV system. So in general, PV systems that are well designed and properly installed require minimal maintenance and have long service lifetime. So the minimal maintenance means you just need to clean up the PV module and do a observation on the PV module. At present, the high cost of PV module and equipment as compared to conventional energy sources is the primary limiting factor for the technology. Consequently, the economic value of PV system is realized over many years. In some cases, the surface area requirement of PV array may be a limiting factor. Large power require a large area of installation. So application of PV modules. In Malaysia, we have two types of PV application. Number one is grid connected PV system, which is the module are arranged in array. So array means the combination of series and parallel string of the PV module to generate electrical energy that sent to the grid through grid inverter. Another one is standalone PV system or off-grid. Standalone PV system have been installed in many remote locations, often because the cost less than power line extension to the nearest utility. So this remote PV system provide electricity for communication station, emergency call box, lights, school and houses. So the modules are arranged in array to generate electrical energy that provide power directly to the load. So here is the PV cell or the solar cell characteristic. Okay. One of the most important characteristic of the PV module is called IV curve. So the curve show the possible combination of current and voltage output of a photovoltaic PV module. Okay, actually we have something, we have error on this figure. So it should be like this. Let me draw. Oops. It's not perfect, yeah? So here we have, so here is VOC. So we have another graph here. Oh, really bad drawing. So this is power at maximum point. So this axis is power. Here is current. And axis here to 0. Okay, this is voltage. So this is VOC, open circuit, which is at current 0. So at maximum power, this is the point, PMP. At the maximum power, we have this voltage. Okay, this voltage here we call voltage at maximum power point, VMP or VMPP. So this is short circuit current. And from this VMP, we have current at maximum point, IMP or IMPP. Okay, same thing. Okay, let's see this definition of the IV and PV curve. Okay, IAC is the short circuit current. This is the current output from the PV cell when the resistance is 0 or short circuit. Okay, that means the voltage is 0. VOC, open circuit voltage. VOC is the open circuit voltage. This is the voltage output from the PV cell when the resistance is infinity. When the resistance is infinity means the current cannot flow, which is I equals to 0. So you get VOC here. Another one is IMP. IMP is the current at maximum power. So at maximum power, here you have maximum voltage here, and this is your IMP. Okay, at maximum voltage and power. This is the current output from the PV cell at the maximum power point. VMP also same thing, the voltage at maximum power. This is the voltage output from the PV cell at the maximum power point. Okay. So this is the maximum power point, so we get maximum voltage here and maximum current here, which is PNP equals to VMP multiply with IMP. Okay. So PMP is the maximum power. This is the maximum power output from the PV cell. So this maximum power generated can be calculated as PMP equals to IMP multiplied with PMP. So this is the equation of power. So the field factor is calculated as FF, field factor, equals to IMP multiplied with VMP. So this is the maximum power over ISC multiplied with VOC. So that one is in this area. So this is also, we have error here on the figure. So your field factor is here. The squareness of the IV curve. Okay. This area only. So it's ratio between IMP multiplied with VMP over ISC multiplied with VOC. So here is the area, the squareness of the IV curve. Okay. So in this figure, so efficiency of conversion. So efficiency P out over P in. So P out equals to PMP, which is equals to IMP multiplied with VMP. Divide with G. G is solar irradiance, watt per square meter. Multiply with area. So area is an active cell, active area of cells, square meter or module area. So usually when we take this value of area, we exclude the frame of the PV module. So PR is the power output, PMP is the peak power from the cell or module, Pin is the power input into the cell or module, which is G, solar irradiance, multiplied with area of the PV module. So this is an example to calculate the efficiency of the module. PR equals to PNP. So PNP equals to 170 watt. Divide with G, multiply with A. Okay, we take G at standard test condition. So G at standard test condition, which is 1000 watt per square meter. And then multiply with area of the PV module. So we don't have area here, it doesn't mention area here. So this one you need to convert into meter. Usually in the data sheet they give in unit millimeter. So to calculate the area of the PV module, so you need to convert to meter. So this is 1.58 meter multiply with 0.8 meter. Okay, because everything in meter, so you need to convert this millimeter value into a meter. So you get 13.45%. So this range we already know that this is polycrystalline PV module, usually. Okay, we end up here. Thank you.